I just want to point out something about monopoles, if they existed, which is a little strange and relates to this, which is that a magnetic field is not a vector. Okay? Well, you can see that from the Maxwell equations, right? Because curl E is dB dt. So if I change x to minus x, E goes to minus E. You can think of this as being, E is really F0I. So I'm doing nothing to time, but I'm reversing space. If x prime is minus x, E goes to minus E. But there's a curl here. So the gradient goes to minus the gradient. And the two combine so that B does not reverse. If you reverse space, the magnetic field does not reverse. Okay, so if I had a magnetic monopole, it looks like this. And now if I invert space, x goes to minus x. Well, this point goes over here, but the B field here would be this one, right? So this under x prime equals minus x would go to this. Would be an anti-monopole. Okay, so under parity, a monopole would change to an anti-monopole. And I think that's consistent with what we were saying before. So just to warn you, magnetic fields are not vectors. You can also see that because magnetic field really comes from these two components. But the way I get the magnetic field is by, I write a bk is 1/2 epsilon kij. And the epsilon comes in. Epsilon under parity changes to -1. Okay, so so magnetic field is not an ordinary vector, it's a pseudo-vector. Okay, so let us continue to discuss these transformations. We've shown that from any solution of the Maxwell equation, by applying Lorentz transformations, I can create an infinite number of other solutions. So that's a lot of symmetry. In fact, so I've already pointed out gauge symmetry. We've got Lorentz symmetry. There's another sort of very almost trivial symmetry of Maxwell equations, which explains the inverse square law. You know, why does the electric charge have the inverse square law? Electric field. What symmetry would explain that? Okay, so I have an electric charge, Q, and the electric field is Q r hat or x hat over 4 pi epsilon naught x squared. That just follows from Gauss's law. Okay. Why is it the inverse square law? What's the symmetry of Maxwell's equations that explains the inverse square law? Okay, so we have, let me just remind you, div E equals rho over epsilon naught. Rho is the charge density, that means the charge per unit volume, etc. So in particular, if I have some solution, I can always rescale the coordinates, right? I can always rescale x mu goes to lambda x mu. So in particular, imagine I just have a point charge, and I rescale my coordinates. Well, think about this as a density. It's really the amount of charge per unit volume. So if I rescale my coordinates, that charge is going to change with the scaling. Okay, the invariant would be the charge, the d3x rho e. This is the q. This is this should be a quantity which doesn't change with the scaling. So that means that if x goes to lambda x, rho e goes to 1 over lambda cubed rho e. Okay, and then obviously gradient goes to 1 over lambda gradient. And so it must be that e goes to 1 over lambda squared e. Okay, so there is a symmetry of the Maxwell equations, where I change everything in this way. I change my coordinates, I change my densities, I change my fields, and the B would be similar, and the J, you can work out what the J must do. So there must be a symmetry. Okay, well, what's the solution for an electric field which obeys this property? There's only one. It has to be inverse square law. There's only one solution, which if I change coordinates, I will get another solution. And it has to be homogeneous of order 2 in X. And so that's the only solution compatible with the symmetry. Of course, I haven't fixed this constant here, but I've explained why it has to be an inverse square law. Okay, so that's scaling symmetry. And in fact, Maxwell's equations have a much, much bigger symmetry called conformal symmetry, and that's also extremely interesting, and it's a lot of people worry about that these days. Conformal field theories you'll have heard of, and Maxwell is the first example of a conformal field theory. Yeah?
What's the difference between the conformal symmetry and scaling symmetry?
Conformal symmetry is much bigger. Okay, so scaling symmetry is a subset of conformal symmetry. So this is obviously only a one-parameter symmetry group. It has one continuous parameter. The Lorentz group has how many parameters in the Lorentz group?
6.
6, right? Because you can see that because it's defined from this equation. This is a constant, and so let's see. The equation is a 4x4 matrix, but it's symmetric. The symmetric should be 6. Let's see. How do we prove 6? Yes, so we have a 4x4 matrix has 16 elements, but a symmetric 4x4 equation has 10 components. 16 minus 10 is 6, I believe. Okay, so this means this is a. That's true. I lie not. 16 minus 10 is 6. So this is a, mu alpha, whatever, nu beta, alpha beta, mu nu, right? There are 16 equations here. But they're not all independent. Why? Because this is symmetric under replacing nu and nu. So there are really only 10 equations here. Why is it 10? Because there are 4 on the diagonal and 6 off diagonal. And these ones are the same as those ones. Right? So there are 10 equations here for 16 things. So there's 6 free parameters. So Lorentz is a 6-parameter group. We also have translations. So that's Lorentz. But I can also do this, where these are constants. Right? There are 4 constants. These are 4 space-time translations. So I have 6 parameters here. I have 4 there. I have 1 here. Okay, but there's a bigger group called a conformal group, which so far I've got 11 parameters. The conformal group has 15 parameters, and it includes things which are more complicated functions than linear. The definition of the conformal group is that that instead of this, yeah, we'll come to it later. It's a bigger group. Okay, it's a bigger group. It's very interesting, and it's.
So it involves like so scaling point.
Yeah. So if you're familiar with complex analysis,
yeah.
where you change when you do conformal transformations, it's the same thing. Okay, so conformal transformation complex analysis change the scales locally, but never change the angles. Okay, and that's what the conformal group does in space-time. It's the same idea, but it's a 15-parameter group in 4 dimensions. But we may come to that later. Okay, anyway, it's just amazing that Maxwell and light really shed light on everything. Okay, and we're still trying to understand what it means. Because this conformal symmetry is certainly very, very, very fundamental. Okay, so where are we? We are... so I want to just mention, this is the Lorentz transformation. These are translations in space-time. And together these are called a Poincaré symmetry. And this was understood before Einstein, that Maxwell's equations have Poincaré symmetry. It's a 10-dimensional group. 10-dimensional Lie group. But what Einstein did was to understand what the physical meaning of these transformations is. Okay, it was understood. This is all just mathematics, but Einstein understood physically the significance, and it was very, very dramatic because it changed our conception of time and space as separate entities. So let us look at an example. Examples of Lorentz transformations. So let's take a sort of trivial example. It's a 4x4 matrix, but let's take one which only involves space. Right? So there's the first row and column are to do with time, and the others are to do with space. So let's just rotate x into y and y into x. And so that means what we'll get here is ct prime equals ct. X prime is cos theta x minus sine theta y. Y prime is cos theta y minus sine theta x. And z prime is z. And then you can easily check that this satisfies the equation. Lambda transpose eta lambda is eta. That's obvious because the only tricky part of this equation is the one with the 0, 0, where there's a -1 in the eta, and that's not involved at all. And so this just rotates. So this is an orthogonal matrix.
One of those signs is positive, right?
Yeah.
Pardon?
One of those signs is positive.
Oh, sorry, you're right. Thank you. So, so that's just a rotation matrix. And as we discussed before, the point about this rotation is that x squared plus y prime squared is x squared plus y squared. It leaves lengths invariant. It also leaves angles. If I have 2 vectors and I take the dot product, that will be invariant. It leaves. So this is an out. Yeah. Okay. Let's leave it at that. So this is a rotation. And it's nothing new. It's what was there already in classical mechanics. But if we do something more interesting involving time, we can't use cosines anymore. We have to use hyperbolic And now the two signs are the same. And so this looks like CT prime equals cos theta CT minus sin theta x. X prime is cos theta x minus sin theta CT. And now what we see is that CT prime squared minus x prime squared equals CT squared minus x squared. Okay, because the cross terms will cancel, and the direct terms I'll get cos squared, CT squared, and then from here sin squared, CT squared, and cos squared minus sin squared equals 1. So that's called a Lorentz transformation. And just as we think of rotations, so let's compare these two things pictorially. So rotation looks the following. So at some point in space with some value of x and some value of y, then you can see that if I rotate my axes in this way by the angle theta, I get the new coordinates x prime and y prime in the formula given above for the rotation. This other one, involving the second Lorentz transformation, or boost, is very similar in that now it transforms x and CT into x prime and CT prime. And the new coordinate axes are not at right angles. Okay? Instead, what's going on, it's quite easy to see that in doing a boost, what you're doing is squashing the coordinate axes on this direction and stretching them on in that direction. Okay? This, of course, is light. This is x, or CT equals x. That's the equation of a light ray, and that is unchanged. So in any coordinate system, if I do any boost, everybody is going to agree that light, so this is also CT prime equals x prime. Okay, so let me just emphasize what this means. I have these two coordinate axes not at right angles, but nevertheless I can label every point in space-time with a value of x prime and a value of CT prime just by drawing lines parallel to this axis, parallel to that axis. I wish I was a better drawer. Okay, and so every point, so this point, for example, has this value of x prime and this value of CT prime. Okay, so it's just a different choice of coordinates on the same space. And it's very clear from these pictures you can never run into a contradiction. And you'll find many papers on the internet claiming that relativity is inconsistent. And usually they always use algebra, and then they make a minus sign error somewhere, and then they get an inconsistency. But if you realize all you're really doing is taking the same space, which is, in this case, just a plane, two-dimensional plane, and here I have coordinates. The original coordinates are coordinates in which time is perpendicular to space, but then I do a transformation where they're no longer, but it's still a perfectly good coordinate system, and nothing can really go wrong. So in particular, let's think about physical phenomena in the two coordinate systems. Well, first of all, who would choose such a coordinate system? So let's imagine we have some observer that used the original system. Okay, like I'm standing here, it's very natural for me to use x, y, and z from, let's say, the corner of the room, and then my time is my time on my clock, and I assume everything that happens in this room I assign some time to. Okay, so that would be, so I would be using coordinates like this, ct and x. But somebody who's moving, let's call them O prime, some primed observer, well, according to me, they are moving along this line, okay, because they are at x prime equals 0. This line here is x prime equals 0. And obviously, they're yeah. If I well, let's just work it out. So we've got ct prime from up here is cos theta. Sorry. So x prime equals 0 means the location of observer O prime, and x prime equals 0 is just x is tanh theta ct, right, from this equation. So according to me, this observer O prime is moving along on that line. And so obviously what I do is interpret this as the velocity. Okay, so v equals tanh theta c, or v over c is tanh theta. So that's what this angle, or hyperbolic angle theta, actually means. It means that it parameterizes how fast the observer is going who's using the primed coordinates. Okay, and tanh theta is always less than 1, and so it follows that Lorentz transformations only allow you to transform to observers moving slower than the speed of light. Okay, and the limit, as I take tanh theta to 1, these two axes are going to become nearly parallel. Sorry, they're going to become nearly parallel and around this point, right? I'm just going to squish these coordinates. This will be my ct prime. This will be my x prime. Okay, so having identified the velocity of the observer who uses the primed coordinates, let's now just rewrite those equations in terms of v. Okay, so if I call these equations, let's call these equations star. Okay, star becomes, you can see from this formula, if tanh theta is v over c, then cos theta is 1 over root 1 minus tanh squared theta is 1 over root 1 minus v squared over c squared, and sinh theta, so that we define in relativity as gamma. Gamma is a function of the velocity v, and sinh theta is tanh theta cos theta, which is gamma v over c. Okay, so equation star just becomes ct prime equals gamma CT minus V over C. Okay, and x prime equals gamma x minus Vt. And those are the usual formulae for Lorentz transformations. Okay, so it was Einstein who realized that these mathematical symmetries actually give you the relationships between measurements made by different observers. So in particular, the two sort of most dramatic effects are time dilation and Lorentz contraction. And so let's first of all think about time dilation. What do I mean by the time? The time is something measured by a clock. And so let's imagine a clock. So what is a clock? A clock is something in which there's a space-time event regularly in time, the ticking of the clock at the same value of x. So I draw my space-time diagram. That's what the XCT diagram is. And these are the ticks of the clock. Okay, so that's a picture of a clock in relativity. Now imagine a moving clock. A moving clock. So what does that mean? It means that the observer O prime is carrying along a clock. This is the O coordinate system. This is the O prime coordinate system. And O prime is carrying a clock like this. And let's assume that the ticks of the clock in the O prime, according to O prime, are separated by some time T prime. This is really CT prime, so these would be CT prime. The ticks are separated by CT prime. And then I want to know, according to me, or observer O, how far apart are those ticks? So, of course, what I do is I draw my time coordinates, and I ask what value of the time does each tick correspond to. So let's in particular just pick this one, and I just want to know what is the value of t corresponding to the first tick of that clock. And so all I have to do is use the fact that x prime is gamma x minus Vt. This is the coordinate of the tick of the clock, is 0, which is just saying this line is x equals Vt. The Ct prime axis is just the line x equals Vt. This is x, T. So x prime is 0, and what about t prime? So now I can express t, or Ct. Yes, I should have written out the inverse of this. Let's see. These imply that Ct is gamma Ct prime plus V over C x prime, and x prime is gamma x plus Vt. Okay, so again, we can express x prime in terms of x, or x in terms of, sorry, wrong way around, x in terms of x prime. And it's fairly obvious that to go for, if you used theta to go from x to x prime, then you use minus theta to go from x prime to x. And so you just reverse the velocity. Okay, so if I want to know where the ticks are in my coordinates, I just have to read off from here. You see x prime is 0. And so t prime, ct is ct, sorry, ct is gamma ct prime plus v over c x prime, but this is 0, and so this is gamma ct prime. So we see that t equals gamma t prime, where this distance here is ct. So it's saying that somebody, if I see somebody moving, right, and the ticks between their, the ticks of their clock are 1 second, according to them, then according to me, they're gamma seconds, right? And gamma is a number which is bigger than 1. Okay, so if somebody takes a year to travel somewhere at fixed speed, and they're going at very high gamma, let's say gamma of 10, then I would say the time I have experienced between two over the 10 years of their time, over the 1 year of their time is 10 times bigger. Okay, so the resolution, the way to remember this is it's always very good to travel. You stay young. Somebody traveling experiences a certain amount of time. Somebody standing still experiences a longer time. So if they go away and they come back, they will be much younger than me. Okay, and we have there are many experiments which confirm this at high accuracy. Particularly the muons arising from cosmic rays in the upper atmosphere would be undetectable on Earth were it not for this effect. So the muons are created in the upper atmosphere, and they decay in some amount of time in their own rest frame. But because they're moving so fast, near the speed of light, it takes them longer to decay in our frame. And that's why they make it all the way down to the surface of the Earth, and then we detect them in cosmic ray experiments. And the gammas involved there are fairly large. I think of order 10 or so. And at the Large Hadron Collider, people are doing experiments where gamma gets up to very large values. Because you can tell that because the mass of a proton is 1 GeV, and the experiments is reaching several TeVs, thousands of times bigger, and basically the gamma factor will turn out to be that number. So the Large Hadron Collider is achieving gammas of 1,000 or 10,000. So that's time dilation. The other dramatic effect is Lorentz contraction. And you can easily, let's first of all I'll just define it. I'm not going to do the algebra. But you can easily do this yourself. But I'll give you another argument for it. So Lorentz contraction means that different observers see rulers to have different lengths, or they see any object to have a different length. Okay, so let's think about a ruler in particular. There's CT and X. So what's a ruler? Well, a ruler you should think about as being defined as a straight line between two ends. So the ends of the ruler would be two lines in space-time. We call these world lines, separated by some distance L. So here's my ruler and with its two ends. Now, the point is that this O' observer Okay, here's O prime, CT prime, X prime. How long is O prime going to, according to O prime, how long is the ruler? Well, you see, O prime is not measuring the length of the ruler at the same times that O is measuring. According to O prime, the ruler starts here and ends there, if I can draw this. Let me expand the picture a little bit. Okay, and then O prime has these axes. So according to O prime, well, this distance is L. But according to O prime, the distance, the length of the ruler is this, L prime. Okay, because O prime measures the length at some fixed time. Measures the distance between the two ends of the ruler at some fixed CT prime. The X prime axis is, of course, just CT prime equals 0. Now, it's easy to see intuitively. You see, it looks like L prime is bigger than L. It looks like you have Lorentz expansion, okay? Because L prime certainly looks bigger than L. But the thing you have to remember is you better calibrate these axes. The units of the X and the X prime axes are not the same. As I mentioned, you've really stretched things in this direction and squished them in that direction. Okay? So the invariant, it's very important to think about invariance. You see, if I was rotating axes, like I did for the rotations, I would say that a distance of 1 on this axis is the same as the distance of 1 on this axis. Why? Because it's just a rotation and lengths are invariant under rotations. Okay, so the two axes are calibrated the same. But in Lorentz transformations, they're not calibrated the same. What is invariant is CT prime squared minus X squared, X prime squared. That's invariant. Okay? So if this quantity is some constant, let's say minus 1, so if I consider in this coordinate system O, CT equals 0, X equals 1, then in the prime coordinate system, it's related to this combination. Okay, that's the invariant. And what that means is that this quantity is the same when, well, this quantity being a constant is just a hyperbola. Okay, so in other words, if this is X, sorry, this is X, this is X equals L, this distance will be X prime equals L, where this curve here is the curve CT squared minus X squared equals minus 1. That's a hyperbola. Okay, so now it's clear that L prime is less than L. Okay, so you have to keep that in mind. So, but I encourage you just to play around with the algebra and convince yourself that rulers really are contracted. But I want to give you a different argument, which is more simple, I hope, than these, based on solutions of Maxwell's equations. So let's imagine we have a collection of atoms. After all, that's what a ruler is made of. A collection of atoms. Okay, and these atoms have electric fields and magnetic fields, but they're certainly solutions of Maxwell's equations. And in particular, just to simplify matter, matters, let's consider some Lorentz scalar, e.g. phi, to be f mu nu, f mu nu. Okay, so phi of x. So what is this? This is minus e squared plus b squared. In fact, I think there's a factor of 2. And so obviously if the atoms are sitting there and I'm just considering the electric fields inside the atoms, and you might, to a first approximation, just ignore the magnetic fields, this quantity varies as I run along the row of atoms. Okay, so at some particular, it won't matter what the function is, but it exists. So as I travel through my ruler, I'm going to see some distribution of electric and magnetic fields, and it's static, just sits there. Static means, so this is phi s of x. It's only a function of x, not t. Now, what do I know? I know that if I do a Lorentz transformation, I'm going to get another solution of the Maxwell equations, right? And the question is, in that new solution, what's the spacing between the atoms? Okay, so it's easy to see the spacing between the atoms will be shorter. Why? Because phi prime of t prime and x prime is equal to phi of t and x, which is equal to phi s of x. That's what we've guaranteed. We've shown the Maxwell's equations are invariant under boosts. So it follows that the solution in the new coordinate system is just equal to this. But now so in particular, this is phi s of x, y, z. But I know phi s. I know the relation between x. X is just given by this. X is gamma x prime plus vt prime. Y prime and z prime are the same. So voila, I have my solution in the boosted frame. It's exactly the same function, but the argument has changed. And now if I ask, what is the distance between the peaks? If this guy had a distance, if phi s has peaks separated by L, by L, okay, then phi prime has peaks separated by, so this means delta x equals L, the change in x is L, separated by delta x prime equals L over gamma. Right? It's exactly the same function, but it's a function of gamma x prime. So the peaks are separated by L over gamma. So that's Lorentz contraction. Okay? So I hope in this way you see that the property of fields automatically gives you all the Lorentz contraction, time dilation. You can work out Doppler shifts of frequencies and all that in exactly this way. So this is Lorentz contraction. Okay, and through the same argument, if I sent some light waves towards you or in any direction, you can do a Lorentz transformation of this sort, and you'll see how the frequency changes and how the wavelength of the light changes. When did we start? We started about 5:02. I'll go for another 15 minutes if you'll let me. Okay. Please scream when you had enough. Okay. Okay, so that's time dilation, Lorentz contraction. All the other effects in special relativity are similar. But of course, there's one formula from special relativity which is the most famous. And that I'm going to pay the most attention to. What's the formula? What's the most famous formula in physics? E equals mc squared. Okay, so let's think about E equals mc squared. And I'm going to show you Einstein's original argument, okay, for E equals mc squared. Neatened up a little bit because he wrote it down in 1905 when he was working in a patent office and he wasn't in an academic environment. And then later in 1947, I think he wrote another kind of popular account and he made it a little bit neater. So I'll give you the neater version. By the way, all this is explained very nicely in Tony Z's book, The Gravity in a Nutshell, which is a very, very entertaining book, actually. It's a very big nutshell. That's the first joke. Gravity in a nutshell is big, but I think what he means is a conceptual nutshell, because it's conceptually GR is the simplest of all theories. I mean, it's really when you understand it, you'll see there's almost nothing to it. But it's just because we introduce these coordinates, and then we have to deal with all of this, the machinery becomes huge. But conceptually, it's extremely simple. Okay, so let's do E equals mc squared, and I'll show you Einstein's argument. So Einstein in 1905, what did he know? And this is the paper I mentioned that is 3 pages long and has no references, okay, and is one of the most important papers ever in physics. What did he know? Well, he knew Maxwell's equations, and he knew all the results of fiddling around with those equations that people had done, engineers had done, because they were beginning to produce radio waves and detect them and so on. And they used Maxwell's equations in electrical circuits and in engineering. So this was already beginning to be quite a developed technology. And he knew roughly, he knew very well what was going on, theoretically. So he knew about Maxwell equations, and that they have a conserved energy. Okay, so light carries energy. That wasn't a big surprise, but of course Newtonian theory couldn't tell you what that energy is. According to Newtonian theory, you cannot have anything which goes at a fixed speed. So you needed Maxwell's theory to figure out the energy. And the energy was known at this time. So I'll call it rho EM. This means energy momentum. You'll see why the momentum comes in, just to distinguish it from the electric charge density. So this is the density in space of the rho EM is the density of, so it will turn out that integral d3x of rho EM equals the energy. In some volume. Okay, so this was known, that if you have a certain volume with some electric and magnetic fields in it, there's a quantity you can integrate over space and it'll give you the energy density. Okay, so this was already known, and this should be familiar to you if you've taken a course in electrodynamics. That's the energy density in the electric field, and a flux, or a current density, J, EM, which is 1 over mu naught E cross B. This is also called the pointing vector. Naturally, we're trying to combine everything into space-time quantities with 4 indices instead of 3. And so obviously you want to rewrite all of this into something with 4 indices. And the way to do it is not... so when we had electrical density, charge density, and current, we combined it into a 4-vector. When you have energy density and flux, turns out that's not the right thing to do. Instead, you combine it into a 2-index symmetric tensor. Called the energy momentum tensor. So actually, before giving that, let me just explain what happened before this notation. They knew there was some energy density in electric fields. They knew that electric and magnetic fields could carry a flux of energy. And the equation that shows this is that dE dt, let's write it d energy dt. So energy was this quantity, energy in volume V. The energy dt is minus integral j em dot ds, where you integrate over some surface. So you have some volume V and a surface S, and the JEM is the flux of energy. So this shows you how energy is transported in the electric field. The flux carries the energy into or out of some volume of space. So that was all known. Now we combine these two quantities not into a four vector, but into a 2-index symmetric tensor called the energy momentum tensor. And this was defined as follows: 1 over mu naught F alpha mu F alpha nu. So we're going to be raising and lowering indices on the F. It's very important to keep track of which index is on the left and which on the right, because it's antisymmetric. Okay, so I'll try to do that. Minus 1/4 eta mu nu F alpha beta F alpha beta. Okay, so the claim is that T00 is equal to rho Em, and T0I, this is a symmetric tensor, T0I is Ti0, is equal to J Em I. Okay, so these are things which Lorentz and other people worked out. That this is the energy momentum carried by the electromagnetic field. Now, why is that an interesting quantity? By the way, the way I'm presenting this, the formulae are kind of coming out of the blue. But when we do general relativity, we'll see how to derive this formula in more or less 2 lines. I mean, it all becomes much, much simpler when you do general relativity. Okay, so for the moment, I'm trying to present things historically. So, there were these formulae lying around in the literature, and it was up to Einstein to synthesize them. But let me just prove that this is an interesting quantity. You see, if JE mu equals 0, if there are no charges or currents, then you can easily show then the Maxwell equations imply that d mu t mu nu em equals 0. Okay, so let's prove that. D mu t mu nu em is 1 over mu naught. Now, I'm taking d mu of this expression. So d mu is a derivative. So first I'm going to differentiate this guy. What does that give me? What is d mu of f alpha mu?
Source?
0.
There's no source, right? So this is 0. Good. So I've used the first Maxwell equation, right? So using the first Maxwell equation, the first term becomes f alpha mu d mu f alpha nu. Right? This is using 1. What about the second term? Well, the second term includes something squared. So I'm going to get a factor of 2, and then f alpha beta. The eta will contract with my d nu to give a d mu to give a d nu, and so that will give a d nu f alpha beta. Okay, so now what do I do with this? Well, my goal is obviously to use the second Maxwell equation, which, if you remember, involves df plus df plus df equals 0. So now I have to try to write all this. So here I've got f times df and f times df, but there's a factor of 2 here. So let's split this into 2. And so I'll write this as f alpha mu times, with a half, d mu f alpha nu plus minus d alpha f mu nu. I can do that because this is antisymmetric under alpha and mu, right? So this expression is exactly the same as this, but with the mu and alpha reversed. And so if I relabel these indices mu alpha and then flip the sign here, I'm going to get exactly the same as that term. Okay, so now I have exactly what I want. I have, this is equal to 1 over 2 mu naught. I'll bring the f outside, f alpha mu, and then reorganize it a little bit. F alpha nu plus d alpha f nu mu. See, what I did here is I flipped these two indices. Mu is on the right, nu is on the right, mu is on the left. So I just flipped them, and I got a minus sign. And then I have the last term here. And again, here I'm going to, let me write it down, and then we'll d nu f mu alpha. Okay, so what I'm doing is relabeling beta as mu. I've got this minus sign. This was alpha mu. But if I flip those two, I'll get mu alpha, and I change the minus to a plus. Okay, but this is exactly Maxwell 2. So this equals 0. Okay, so using the two Maxwell equations, you can show that d mu t mu nu equals 0. And this is enough to tell you that okay, Ti0, of course it's symmetric, so it doesn't matter. But this implies that equation, which is that the rate of change of this density is equal to the divergence of this flux. And this is enough to tell you that if the energy is defined to be integral d3x t00 em, then d by dt of the energy, I'm allowed to take this ordinary derivative under the integral, and it becomes a partial derivative, because this is a function of t and x, a partial derivative only with respect to t. So this is equal to d naught t00, or dt, let's call it, t00 of t and x. And this is equal to, naught is ct, remember, right? So this is 1 over c dt. And so this would be minus c integral di t0I d3x. And then we use divergence theorem to say this is minus c integral j I ds I over some surface where ji is t naught I over c. And similarly, d naught of t naught I, I take the I components of this equation. There are three more equations. This is the 0 component. This would be minus dj of t ji em. And so similarly, you can see that pi is equal to integral d3x t naught I obeys a similar law. And so from this, you basically get expressions for the energy and the momentum in an electromagnetic field. These can be combined into p mu, which is a 4-vector, where p mu equals 1 over 6c integral t gamma mu epsilon mu nu alpha beta dx nu dx alpha dx beta, and this is the energy momentum 4-vector in the electromagnetic field. So in particular, I'm not going to use this expression, but it's nice to know it exists. In particular, let's consider our plane wave. And B equal to 0 minus f of x minus ct over c, 0. Okay, so we showed that this is a solution of the Maxwell's equations. It's a wave traveling in the x direction with the electric field in the z direction and the B field in the negative y direction. And now we can just calculate t naught naught is equal to f squared over mu naught c squared, and T0x rather, the flux of energy in the x direction is f squared, is also f squared over, is the same thing. So just as before, when we combine objects into a single object, like T mu nu, the dimensions of the single object, every component, the dimensions must always be the same. And so you see that this T00 and T0x are, have the same dimensions. And then we can see that the energy carried by the plane wave is just the area, the transverse area, in other words, the integral dx dy, dy dz, times integral dx, f squared, epsilon naught. 1 over mu naught c squared is equal to this quantity, so 1 over mu naught c squared equals epsilon naught. And the momentum p x is equal to, put it there, px is equal to the same thing with a 1 over c. Px is area over c times integral dx f squared. So what we see is that for a plane wave, for momentum, p gamma is equal to E E over c p 0, 0 with E equals p over c. Okay, so from all of this, you can calculate the energy and the momentum in the plane wave, and you discover that the energy and momentum are just related by this formula. Now, c has to be there for dimensions. Momentum is mass times a velocity. Energy is mass times velocity squared. So this much was known. That electromagnetic waves carry energy and momentum, and they are related in that manner. So I've gone on too long already. Let me just see. Yeah, so I think let's start next time. Let's do E equals mc squared next time. All we'll need to know is that light waves carry energy and momentum in this relation. Okay, and then Einstein's proof of E equals mc squared just involved thinking of an atom which emits light waves, and then requiring that that physical process is the same for all observers. And just from that, he could show that there's the relationship between energy and mass of the particle. Okay, yeah, any questions?
I just got really lost over this way.
Okay, sorry, a lot of algebra. So are you happy with this derivation?
Wouldn't mind going through it one more time.
Okay. So what I described is that in the 19th century, people knew that electromagnetic field carried energy and flux of energy, right? The Poynting vector. then it was realized that you could combine those two objects into this guy. You notice it's quadratic in the E's and B's. And then if you calculate the 0, 0 component, let's do that, for example. So 0, 0 component here, what do? I calculate 1 over mu naught, F0, that index, the mu is 0, the nu is 0. This is antisymmetric, so I only have to include the i's. Okay, so that's the first term. The second term is plus a quarter. And then here I have f 0i, f 0i. And then I have fi0 plus fi0. And then I have plus fij, fij. These are all possible indices that will give non-zero results. Okay, so when you combine these terms, this one is essentially going to give you b squared. Remember, fijk was bk. And all of these terms are going to give you e squared. And so, so we get this equation up here. Okay? So I've defined this messy thing involving f. Its 0, 0 component is precisely the energy density in the electromagnetic field. And its 0I component is precisely the Poynting vector. Okay, so it's a unified expression. This somehow incorporates both of those things. Now, why is it so then what I proved is that this expression obeys this simple equation. And we call this, we say that the energy momentum tensor is conserved if it obeys this equation. Okay, this is an equation for a conserved tensor. Why do we call it conserved? Well, if we have such an equation, we can write it this way, which means that time derivative of its 0, 0 component is the negative of some divergence. And as soon as I have a divergence, I know that if I integrate over space, I'm only going to get a surface term. So it's saying that, imagine there's no surface term. I have some local process and nothing's going on the surface. Then this will be, then the surface term will be 0. It means that the energy within this volume is conserved. Okay, so people knew that from this T mu nu, you can derive a conserved energy for the electromagnetic field. So all of this is just all of this is just a fancy rewriting of that. And so yeah, and in fact, I wasn't, this is a bit of a diversion, okay? You can just disregard that if you like. All I'm showing there is that you can combine the notions of energy and momentum into a tensor. But for the purposes of this argument, all of this is just a side issue, right? It's really, I'm just trying to, I'm trying to combine things into, space-time tensors. The really important formulae are these two. One of them is the energy density, and the other is the flux of energy. From those quantities, let me see, that's not quite true, because, I'm sorry. Over there, I've motivated the energy, right? This is the energy. It turns out that this flux is also defines a momentum. So that's what. So the integral d3x of t00 is an energy, the integral d3x of t0I defines a momentum. Okay? And this equation, d mu t mu nu equals 0, there are four equations here. One is an equation for the 0, 0 quantity. That'll tell me energy is conserved. The other equation is for the quantity with an I here, and it'll give me the conservation of momentum. Okay, so this was basically known, but in this other not relativistically invariant form. Expressing it this way simply makes it more compact. Okay, so for example, I haven't really written out the you know, when I just told you that this P equals to this obeys a similar equation. That you can see because d by dt of this, right, is d by dt, so it's proportional to d naught of t naught I. And we know that d naught t naught I is equal to minus dj tji, so that again is a divergence. And that again will give me some surface term involving the space components of the stress energy tensor. But at the end of the day, all you should take from this is that people knew this formula. Okay. Okay, they knew that electromagnetic waves carry energy, and they knew they also carry some conserved quantity like a momentum, and these two things are related by E equals PC. Now, as I said, when we understand this a little more deeply, this will all become completely obvious. Right? So in a way, all of this is just an excursion to say that things were rather complicated before they were understood. And when they were understood, this becomes easy to see. You see, the interesting thing has happened. This wasn't even understood by Einstein in 1905. He didn't know really why there is such a thing as an energy and why there is such a thing as a momentum. Who's the person who understood that? Who understood what energy is and momentum is? This is somebody who's much less recognized than he or she should be. Emmy Noether. Okay, so Emmy Noether in 1917 realized that conservation laws, conserved quantities, are a result of symmetry. Okay, and that wasn't really appreciated before. And we'll do this, I think, next time. We'll certainly do it tomorrow. We will derive. There are 2 lectures tomorrow, so we'll understand tomorrow. Where do these conserved quantities come from anyway? All right. Why is there a thing called energy? And when we understand the why, it'll become much easier to see, you know, why this works. I mean, here I had to just do some manipulations. Why did all this work? Why did I get some quantity that was a divergence? I had to integrate it, blah, blah, blah. Okay. The reason for it is symmetry. And the symmetry is amazing, okay? Do you know can you guess? What is the symmetry that gives rise to the conservation of energy? What's the symmetry? There's some symmetry. It's a statement about the universe. What's the difference between the universe today and tomorrow? Is it very different? Not very different. Okay, that's why energy is conserved. Because the universe today and tomorrow are more or less the same. But actually, they're not exactly the same, because the universe is expanding, and that you see that energy is not exactly conserved. All right? So Noether realized that the symmetry under time translations, it's exactly the Poincaré, the 4 parameters corresponding to translations in space-time. They give 4 conserved quantities. The time translations gives energy. The space translations give momentum. Okay. Now, I also told you something about rotations. Well, the world is pretty much rotation symmetric, right? If I take the universe and I rotate it, looks pretty much the same. What is the corresponding conserved quantity? 3 of them, because there are 3 rotations, there are 3 Euler angles. Pardon? Angular momentum. Okay, so that's also a consequence of symmetry. So all conserved quantities we know about are consequences of symmetry. Do you know why is electric charge conserved? Gauge symmetry. But I told you gauge symmetry. Okay, now, but remember, that why did gauge symmetry work? Gauge symmetry worked because this was antisymmetric, right? So the 2 terms cancelled. When I took A to A plus dA, the 2 terms cancelled, only because of antisymmetry. But remember Maxwell's equations, d mu, f mu nu is something, mu naught, j nu. This is antisymmetric. Okay, so if I do this, I get that, but this is identically 0, right? Because this is symmetric, that's antisymmetric. So it must be, so Maxwell's equations imply this. But that's a conservation law, because now I can take integral j naught, and d by dt of it is equal to integral minus d3x di ji, and that's a surface term. This is electric charge. So electric charge is conserved because of gauge symmetry. Okay, and so next time we will actually prove Noether's theorem and see, it's a kind of formal exercise, but we'll see that every time you have a symmetry which is continuous, you always get a conserved quantity. And ultimately that will be the explanation of the E equals mc squared. Then we will really have a one-line derivation, E equals mc squared, because we know what energy is. You need to first know what is E. When you know what E is, then you can just calculate it for anything, and we'll get E equals mc squared. Okay, apologies for all the algebra.